Most stars live quiet lives. They shine, they age, and slowly fade away. But some stars end in ways that are anything but quiet. When a massive star runs out of fuel, gravity takes over. The core collapses in a fraction of a second, while the outer layers explode outward in a supernova. What remains is not always a black hole. Sometimes the collapse stops just short of total destruction. What's left behind is one of the strangest objects in the universe: a neutron star. A neutron star contains more mass than the Sun. Compressed into a sphere only about 20 kilometers wide. The collapse is so extreme that atoms are destroyed. Electrons are forced into protons, forming neutrons. Almost all empty space inside matter disappears. If Earth were compressed to this density, it would fit inside a city. A single teaspoon of neutron star material would outweigh a mountain. This is not normal matter. This is matter pushed as far as physics allows. The surface gravity of a neutron star is billions of times stronger than Earth's. Its crust is a solid lattice of atomic nuclei, locked in place by gravity. Below the crust, neutrons flow in a superfluid state. At the center, we are no longer sure what exists. The physics becomes uncertain. Neutron stars sit at the edge of what we can describe. But size and density are only part of the story. When neutron stars are born, they often rotate extremely fast. As the core of the original star collapses, it spins up, like a figure skater pulling in their arms. Some neutron stars rotate hundreds of times per second. With powerful magnetic fields, they emit beams of radiation from their magnetic poles. If one of those beams sweeps past Earth, we detect a pulse. These objects are called pulsars. A pulsar is not a different kind of star. It is a neutron star, seen from the right angle. Some pulsars are so stable that their pulses rival atomic clocks. They tick with astonishing precision, unchanged for millions of years. Some pulsars exist in tight binary systems. One extreme example is known as a black widow system. In these systems, a pulsar orbits a small companion star at close range. The intense radiation and particle wind from the pulsar slowly strips material from its companion. Over time, the pulsar effectively consumes the other star. These systems show how violent a neutron star can be, even long after the supernova has faded. Not all neutron stars are defined by rotation alone. A small fraction are dominated by magnetism. These are magnetars. Magnetars possess magnetic fields trillions of times stronger than Earth's. So strong that they can distort atoms and tear apart molecular bonds from vast distances away. The crust of a magnetar is under constant stress. When it fractures, the star releases a sudden burst of energy, a star quake. These eruptions release intense gamma rays, sometimes detected across the galaxy. For a brief moment, a magnetar can outshine everything else around it. We don't usually see neutron stars directly. They are too small and too distant. Instead, we detect them by what they emit: radio pulses, X-rays, gamma rays. One of the instruments that transformed our understanding of these objects is the Fermi Gamma Ray Space Telescope. Fermi revealed that many pulsars shine brightest in gamma rays, not visible light. It helped identify magnetar flares and track violent high-energy events across the universe. Through instruments like Fermi, we don't just see stars, we see their most extreme behavior. Among the strongest signals we detect are brief flashes of gamma radiation. Some of the shortest and most intense of these flashes are produced when two neutron stars collide. In these moments, space-time itself ripples, producing gravitational waves. For a few seconds, more energy is released than the Sun will emit in its entire lifetime. These collisions also create heavy elements, gold, platinum, and others, scattering them into space. Not all gamma-ray sources are neutron stars. Some come from far larger systems. Blazars are active galaxies with supermassive black holes at their centers. They launch enormous jets of particles moving near the speed of light. When one of those jets points directly at Earth, we see intense gamma radiation. Blazars remind us that extreme energy exists on many scales, from city-sized neutron stars to galaxies billions of light-years away. But neutron stars remain unique. They pack stellar mass into planetary size and turn collapse into precision, violence, or both. Neutron stars, pulsars, and magnetars are not separate stories. They are the same object, shaped by mass, rotation, and magnetism. Some spin quietly, some tear apart companions, some crack their own crust and flood space with gamma rays. When massive stars die, they don't always vanish. Sometimes they leave behind objects so extreme that even the universe seems to hesitate around them. Thank you for watching. See you in the next video.